Welcome, ladies and gentlemen, to this presentation entitled Comparison of Measured Static and Quasi-Static Deflections of Industrial Manipulators. This work is presented at the 14th Virtual LAM211 Conference and Exhibition. My name is Nicholas Tyson, and I co-authored this work with my colleagues Monica Katharina Gonzalez and Theodoros Laspas under the supervision of Professor Andreas Akenti. This presentation consists of 4 sections. The introduction section focuses on performance criteria and test methods according to ISO 9283, which can be used to identify performance criteria when the robot is carrying a payload, and performance criteria such as quasi-static deflections, which can be used to assess the robot in a contact application. The main section is the methodology section. It presents measurement instrument and procedures for both the static and quasi-static deflections of industrial manipulators. The results and discussion section focuses on the application of the proposed comparison implemented in a case study on a large-sized serial articulated manipulator in 3 different positions of its workspace. The presentation ends with a summary of the proposed methodology. It outlines its opportunities and limitations, as well as the next steps to support compliance calibration. Introduction section. ISO 9283. According to the information provided by the International Federation of Robotics, most industrial manipulators are used in tasks in which the manipulator carries a payload. In this case, kinematics, gravity torques, and controller settings are the most important performance criteria to assess the applicability of an industrial manipulator for its intended purpose. These tasks are reflected through performance criteria such as pose as well as path, accuracy, and repeatability. These indicators are commonly stated in the product descriptions of the manufacturers of industrial manipulators. Poses are measured at targets with a static manipulator, while paths are measured under motion with the manipulator following a trajectory. Figure 1 visualizes potential poses and paths according to the recommendations by the ISO standard. However, these performance criteria, according to ISO 9283, are less informative when the manipulator is engaged in a contact application such as metal cutting. Contact applications. Metal cutting, such as trimming, grinding, or deburring, can be considered a contact application. There exists no standard about the evaluation of performance criteria of industrial manipulators in contact applications, as it is only a minor share of manipulators that is installed for that purpose. Of the shipments of industrial robots from 2011 to 2015, it was only approximately 1% of the robots that were installed for metal cutting as their intended use. Due to the absence of a standard, researchers are inspired by the state-of-the-art of performance evaluation of lathe and machine tools, and one of the main criteria under investigation is compliance or stiffness. The stiffness of a mechanical system can be defined as its capacity to sustain loads. There are a priori modeling approaches employing finite element analysis that are usually reserved for robot manufacturers and researchers, and a posteriori measurement approaches to evaluate compliance or stiffness. There are online approaches that identify the stiffness of an industrial manipulator from features of a machined workpiece, and there are offline experimental approaches. This work focuses on offline experimental approaches. Serial articulated manipulators in quasi-static contact applications. So, ISO 9283 provide guidelines for the measurement and evaluation of static compliance. This is representative of a robot carrying a payload. However, this work intends to emulate the quasi-static component of a metal cutting process. This can be seen in the picture in figure 3 on the bottom side of the slide, where the quasi-static component and the dynamic component of the machining force are qualitatively highlighted, and the quasi-static component of the process force consists of the slow and periodic force with a frequency lower than 0.5 Hz. Methodology section. Measurement instrumentation. The conceptual measurement setup can be seen in Figure 4 on the right-hand side. The setup comprises the following equipment. 1. A large-sized serial articulated industrial robot with its corresponding controller, which is not included in the picture. Number 2. A Leica 18901 laser tracker, which is also not included in the picture, but which is represented by a 0.5-inch spherically mounted retroreflector. Number 3. The measurement instrument loaded double ball bar with an LVDT mounted inside. A rigid table link, number 4. And number 5, a dummy end effector with a tool center point and a mechanical interface for the spherically mounted retroreflector. The deflection measurements are performed with two different metrology loops. That is, the first metrology loop uses the LVDT, which is inside the LDBB for the deflection measurement, and the second loop uses the laser tracker. Measurement process. The procedure for both the static and quasi-static measurement is repeated at 3 positions numbered as circle 1 to circle 3. The circles have different radii, r, from the origin of the robot's base coordinate system. This is visualized in Figure 5. All circles have the same z-axis component or height from the ground. The circles have a diameter of approximately 250 mm. For the static measurement, the manipulator moves to a static configuration, then the robot is loaded with a force, then the robot is unloaded. Finally, the robot moves to another static configuration, then the procedure is repeated. The static measurement measures static deflections at 37 index positions along a circular trajectory. This is indicated in the circle in the right-hand side in the top corner. For the quasi-static measurement, the manipulator moves to a start configuration, then the robot is loaded, then the manipulator moves along the circular trajectory, and only after completing the trajectory the robot is unloaded. This dissected the circle into approximately 16,000 measurement points. Both measurements induce loads of 125, 250, 375 and 500 Newton. For both the static and the quasi-static measurement, multiple force components were exerted simultaneously, as can be seen in the right-hand side of Figure 5. Let's watch a video of the measurement process. Let's start with the static case, where we move, load, unload, and move to the next configuration. So the robot moves to the first configuration, then it is loaded, unloaded, and it moves to the next configuration. Once again, the robot is loaded, the measurement is taken, it is unloaded, and it moves to the next configuration. And the same thing is repeated over again for the 37 configurations. Then, in the quasi-static case, the robot is loaded, it moves along the trajectory, and only once it has concluded the circular trajectory it is unloaded again. In this case, the manipulator moves twice clockwise about the circular trajectory, that is, that we have measured with an angular overshoot of 180 degrees to exclude transient effects from the measurement data. The Cartesian velocity of the robot is 50 mm per second in this case. Data analysis. The deflections delta x are calculated as the position differences of the loaded TCP position, which we can refer to as xij, compared to the reference TCP position, which is referred to as xiref, at a load of 125 Newton. All deflections are calculated relative to a reference load of 125 Newton to remove the influence of the play in the setup, the kinematics of the manipulator, as well as backlash in the manipulator. The indices I and the loads j represent the position and loads. That is, there are 37 static configurations and there are 15,899 quasi-static configurations. For the quasi-static deflections, one has to remove the angular overshoot, and in both cases, the static and the quasi-static, the measurement data from the LVDT needs to be compensated for the deflection of the table link. The magnitude of the deflection, which is referred to in the subsequent section, is calculated as the Euclidean norm of the deflection. In the following section, the wording apparent load is used to highlight the idea that everything is calculated with respect to a reference load of 125 Newton. That is, when in the next section we will talk about an apparent load of 125 Newton, it means that the system is actually loaded with 250 Newton, but the difference with respect to 125 Newton is considered. Results and discussion. Case study. The magnitude of the static and quasi-static deflections along circle 1 for apparent loads of 125, 250 and 375 Newton can be seen in the tables on the bottom. The magnitude of the deflection, as one would expect, increases with the load, but also changes along the circular trajectory as the Cartesian stiffness of the industrial manipulator depends on the configuration. The table shows the acting load in the first column, the static deflections as measured by the LVDT and the laser tracker, and the quasi-static deflections as measured by the LVDT and the laser tracker, as well as their quotient. Here we find the same data for the second circle, and here we find the same data for the third circle. The measured quasi-static deflections are on average approximately 22% bigger than the measured static deflections. The quasi-static deflections are at most 32% bigger than the static deflections. For all acting loads and all circles in the case study, the quasi-static deflections are bigger than the static deflections. The data have been measured using the LVDT as well as the laser tracker. The difference in the measured LVDT and laser tracker data can be accounted for by the distance between the measurement points. The static and quasi-static deflections are similar in their characteristics, but they differ in their magnitudes. Outlook. Why and what next? The result displayed in the tables imply that there can be a significant difference in the magnitude of the static and quasi-static deflection. It needs to be pointed out that there is no apparent determinism that leads to the observed difference. That is, the observations of this case study cannot be used to derive useful information about the serial articulated manipulator. One cannot even derive further information about the remaining workspace for the investigated industrial manipulator. Further investigations require the analysis of the influence of the Cartesian velocity in order to consider the influence of friction, as well as different controller settings in terms of the operation mode and the task program on the difference between the static and the quasi-static deflections. Nevertheless, the case study shows that the loaded circular testing is capable of accurately identifying the deflections of the industrial manipulator along a circular trajectory. This may facilitate a pragmatic compliance calibration approach of industrial manipulators. The pragmatism in that sense lies in the possibility to calibrate an industrial manipulator task-dependent, that is, for the relevant portion of its workspace, with loads in the magnitude of the task, rather than workspace-dependent. This makes compliance calibration potentially cheaper, faster, and more accurate. This concludes today's presentation. Thank you very much for your kind attention.